Thank you very much. Thank you, Jens, for the kind words, for the kind presentation, and good morning, everybody. It's a bright and very snowy day in Stockholm, but my understanding is the audience is distributed across Europe, so probably your situation is very different. Still, welcome. It's the third day, so you've gone through quite some presentations and sessions by now. So I'll try to be very generic, very broad, cover an area that is probably going a bit outside of traditional computational neuroscience or neuroscience at all, which is going to industrial or technical applications. So the keyword is robots. And I will first spend some minutes explaining why I care about brains and robots, and then give some examples of sensory systems, of sensory processing, of motor systems, of closed loop systems, and where we want to go in the future. So this is a 45-minute session. It's a presentation. I'm not used to talking 45 minutes by myself. So now I hear this is a different setting with a live stream, with a delayed live stream. But please, you're more than welcome to ask questions in the chat anytime. If you feel this is an important question to be addressed right away, indicate that, maybe with 5 stars or something, and Jens might decide to pick it up. And then we can inject the question during the presentation. Otherwise, we have time at the very end. Now, again, a few more brief words about myself. So I've studied computer science and electrical engineering. Then I decided to do a PhD in computational modeling, computational neuroscience in Zurich, because I wanted to better understand how neurons compute and why there is this magic happening in our brain that allows us to interact with our world, to do everything that we do. After that, I founded a group in Munich about scientific system theory, neuroscientific system theory. So first, connecting neural systems to robots. And recently, 2.5 years ago, I transitioned, I moved to Stockholm, set up a new group. That's why on the introductory slides, you see there's a small group at KTH now, but we're expanding. And there have been many people contributing to the work that you will see over the last 8, 9, 10 years in Munich. If you want to read up more about what we do, there is a web page that is called neurocomputing.systems. So you can get some ideas of what we do. Now, most of the presentations I talk to either neuroscientists or to computer science or engineering people. And I have to introduce either the brain or computers to all these audiences. Now here, it's probably a mixed audience, so where we have people who know a lot about the brain, and we have people who know a lot about computers. So I will use this first slide to refresh your understanding about aspects, about computational aspects in brains and in computers. If you look at the left side, this is information about your brain. So on this side, you see it's about 1.3 kilograms. It has 100 billion neurons. That's a very big number of neurons. But again, I'm preaching to the choir. Most of you know that we have very many neurons. But neurons are not there from the very beginning. They grow. They start from a single neuron upon birth, and then upon pregnancy, and then they grow and build more and more and more neurons into that functioning brain. Now, the sad news is that in my age, maybe starting at your age, but definitely in my age, we also lose neurons. So we lose about 1 neuron per second. So that's like now, and now, and now, and now. So it's a highly flexible computing system that adds neurons and works, and that loses neurons and works. It's not that I'm degrading my brain's performance noticeably every second. You all know how neurons work. They're basically analog, leaky, integrated fire devices. They communicate with spikes, with pulses, digital pulses. They communicate through synapses to other neurons. These are stochastic, so they're not reliable. There's no guaranteed transmissions. And neurons typically operate at very low firing rates, 10 hertz, something like that. Now, computers on the right side are very different devices. The weight of the processing unit of the CPU inside your computer is largely irrelevant, but it's much less weight than your brain. It has a roughly similar number of transistors. Now, you see this number is pretty outdated. By now, we probably also have on the order of 10 to the 11 transistors in our computing devices, in our chips. Of course, a transistor is not the same as a neuron, but those of you who work in neuromorphic engineering, they know, or you can, with just a few transistors and a capacitor and some very small components, you can build systems, you can build computing devices that operate very similar to what a single neuron does. So the punchline here is, we are getting to that number of neurons. We're probably not there, but we could go to a roughly similar number of neuron-like computing devices in our chips. If you think of computers some more, in our engineered systems, we really don't want any modifications over lifetime. So if we have running software and we want to store data today and tomorrow and next week, we want to be able to store data at the exact precise location on a hard drive. We don't want it sometimes to work and sometimes to not work, or change the routing path of data all the time. We as engineers, we don't know how to handle systems that are unreliable. How do computers work? Of course, it's all digital Boolean logic. We have reliable digital signal processing and proper propagation. We have reliable storage, and they typically operate very, very fast. If you buy a computer that operates at 100 Hertz, you're waiting until next week to start your operating system. Computers operate at gigahertz clock rates. So it's fundamentally different computation in brains, in wetware on the left, and in computers and machines on the right. Now, what we try to do is we try to understand principles of how computation in brains work and apply this use this in technical systems, such as the computers on your desks, or more specialized, more dedicated neural-like hardware, so that we can copy, we can reproduce, we can mimic some of the functionality that brains have in technical systems. Our main goal is not to understand the brain, and would be very brave for me or my students to claim that we will likely understand the brain. Our goal really is to use understanding of how the brain works, fundamental principles of how the brain works, so that we can advance technology, advance technical systems. So before I give you some examples of that in the next half hour, 40 minutes, let's look at the bottom diagram where you see neuron count over animal species. There are several very remarkable spots on this diagram, on this growing number of neurons. It's on the very left with a sponge and a very few neurons. It's in the middle, and it's on the very right. So let's look at the left and the right first. The left one is really funny story that I've heard. So there's this sponge, this seashell animal that upon birth has a number of neurons, not very many, a couple of tens of neurons, and it happily swims in the ocean to collect food. But then at some point, the sponge decides to attach to a rock and stay there at the rock. And the next thing it does is it eats up its own brain. So it digests its own neurons. Now that is a very smart thing to do, because the neurons are very nutritious. They can generate a lot of energy for the body. That's also a very stupid thing to do, because when you eat up your own brain, then what do? Well, I just said that you stay at the place for the rest of your life, and instead of actively going after your food, you wait for your food to swim through you and digest whatever happens to arrive at your place. So some of my previous students said that this is very similar to professors who get a permanent position at some university, but that's again a different story. So what I want to highlight here is that the sponge seems to decide that it doesn't need a brain when it's not actively interacting within its environment, when it's not purposefully doing actions in its environment, such as hunting food. And if you think more about it, this is exactly what brains are made for. We use our brains, all the animals use their brains to perceive information from the environment, let's say visual or tactile or auditory information, process this, so understand what this means for themselves, and in the end, they produce motor output. Brains are not meant to do, handwritten digit recognition or computer vision obstacle avoidance tasks, just to do handwritten character recognition. They are really meant to produce motor outputs so that we, I, you, everybody can optimize your chance of survival and reproduction in the world. So the brain is all about long-term optimization of motor outputs. And that's why I care much about brains, because that's also what I want to do in technical machines. I want to build machines that are better interacting, that are better understanding the world so that they can interact in the world. And you will see plenty of robots on the next slides that we build, that we use to interact in the world. Now, if we want to interact better in the world, one thing we could do is use more neurons, use bigger brains. And now I want to point you to the very right of this diagram. So if you look at neuron count at the very high range, we humans tend to think that we are the crown of all and we are the most intelligent beings on the planet. But it turns out by far we don't have the largest number of neurons. It's elephants that have about 10 times more neurons than us. They're obviously very intelligent animals. They can remember many things. They can act and interact purposefully in their world. But we think we are more intelligent than elephants. And the take-home message here is that it is obvious that not only neuron count matters. It's clearly helpful to have more neurons. That's why we are more clever than frog or mice. But it's not only neuron count. It's probably also connectivity. It's probably also how they are connected, how efficient they are connected. There's plenty of other aspects to look into rather than the sheer number of neurons. The last part I want to look at is somewhere here in the middle. So when I said earlier, oh, we have computers that have 10 to the 11 transistors nowadays, we don't really have that available. We could build such neural style computers if we had lots of money and expertise and time. What we do have available is general purpose computers. And if we run these general purpose computers really fast, either your GPU equipped machine or some supercomputers, we can absolutely simulate in software a large number of neurons, let's say 10 to the 7, 10 to the 8, probably up to 10 to the 9 neurons. We can simulate in general purpose computers in real time these days. So it's not a question of brute force computing power that we are lacking, because we don't see systems like artificial cat walking around in the world. We don't have mobile robots that are as clever as cats. And I'm not talking of mechanical limitations. You've probably seen videos from Boston Dynamics of amazing robots that jump and walk and hop, and we see some more robot videos later in the talk. What I'm referring to is that we have the brute force computing power to real-time compute large neural networks if really needed, but we don't have the same level of intelligence in machines of, let's say, everyday real-world intelligence that we observe in cat or similar animals, the adaptability, the understanding of environments, and so on. So we are missing more than just brute force computing power. Okay, now I've spent a lot of time introducing why I'm excited about this topic, because I really want to understand what makes neural computation so efficient in understanding the world and in operating on sensory data so that we can produce motor output. And the way we do this is summarized on this slide. So we have a number of different robotic systems. There's, as examples, there's a robotic arm shown here. There's a mobile robot with onboard neural computation. There's a mobile robot with distributed external computation. There's only sensors and actuators, the wheels on board. We have flying robots because many labs are interested in flying systems. They mimic what bees do. So they need to trade off brain size, weight, computation loads, because they have to carry all their computation on board. And it's expensive to carry large computers, both in terms of weight and energy consumption. So we have different robotic systems that we investigate, that we apply so that we can investigate neural computation to control them. And the two aspects I want to focus on this talk today is event-based neuromorphic vision. I want to give you an understanding of what vision systems derived from how brains or how eyes see and translate information to brains, how these vision systems work. I want to give you some understanding of challenges and opportunities in here. And I want to talk a bit about real-time computing and control in the neuromorphic domain. So how can we allow systems to run in real time so that they can interact with the world? So let's start with topic 1, event-based neuromorphic vision. What is neuromorphic vision or event-based vision? So everybody among us is so used to cameras these days. In fact, in every mobile phone, everywhere there are cameras. I use a camera on my laptop right now to talk to you. We are so used to cameras that we think our eyes work like cameras, but they don't. The photosensitive elements, the rods and cones in our eyes, in essence, transmit change information to the brain only. So what I mean with this is that every single photoreceptive element, every pixel of our camera, of our eye, if you wish, observes a particular area in the field of view. And if lightning changes in that area, then there is a spike. There's a neural communication going from eye to brain, saying, oh, here something has changed. Now, in the video at the bottom, you see the same effect shown in an artificial sensor that mimics this behavior. So on the left, you see a traditional video recording of my hand moving up and down. There's a half white and half black background. This is what we know from video images. On the right, you see the same scene recorded by an event camera where the static background is completely ignored. And you see only when my hand moves into a particular pixel's field of view, there's an event generated, shown here as a red or green dot. So this camera, this event camera that we reconstruct as a video on the right, this event camera only provides spike information about places of change, of changed illumination, of changed light intensity in the world. So when my hand moves in, it's getting darker or brighter, we get an event. This has quite a few advantages. So for example, we're getting significantly fewer events rather than full video images out of the system. It responds right away. So all these pixels speak up and say now, 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 right away when something happens. And each pixel has a significantly higher range of responses, meaning that if you have global illumination in the whole scene, a camera is likely to either oversaturate or undersaturate. Whereas here in the event cameras, we have individual pixels that receive, that observe changes of light and then send out spikes depending on their temporal change. So if it's very dark or very bright, or at some place very dark, at some other place very bright, all these pixels respond. On the right side, you see a different drawing of the same scene. So here on this red shown axis, you have time in milliseconds. And on the other two axes, you see the pixel space, X and Y of the camera. So when I move my hand up and down, you see there is a steady train of events. This could be red or green, as shown here, or it's just a black dot that represent over quasi-continuous time, single events. So that's the data format we're getting. I have one more slide to show this. This again is a video reconstruction of my camera when I move it around in my office. But this is a video reconstruction of these events so that we believe we understand what we are seeing, a desk and a shelf and a door. In fact, this camera produces single events one after the other, as shown on the right. So at this point in time, we're getting an event, say a positive spike at this coordinate. At the next time, we're getting a negative spike at this pixel coordinate and so on. The time is implicit. We can observe the time at which the event occurs. And but it's not reported by the sensor element itself. The sensor, so the pixel just spike at the time when they spike. So this is the data format we are getting as input into our processing system. And you can think of these as individual spikes on individual dendrites going into a computing system. So if you want to use such a camera, you can go to companies, for example, Innovation, and you can ask them to sell such a camera to you. You can buy an event camera nowadays. Those all come with a USB cable that goes into your computer, and that's great. for development. So you can do recordings, you can run this into your processing algorithms. But what we want to do is we want to run the same systems, we want to operate these systems on board of robots. And therefore, we've built embedded prototypes where you have the same chip integrated in either such a more complex system with onboard computation, or a lightweight, very small system with onboard computation. So we have embedded microcontrollers or processing systems that can run neural networks. And these computing systems are directly coupled to the sensor, so that coming from the sensor input, we can process, we can compute meaningful output and drive motors and act in the world. So what we do with this, here are several example projects. There is a mobile robot chain where one robot can follow the other robot. So you see there's 3 robots following each other. The last robot has a little normal camera, a default camera, a GoPro on it, so we can record this video. The first robot is remote controlled by a student. So it's a very intelligently driven robot by that student. And the other robots simply follow because they observe the blinking light of robots up front, and they can track and follow these lights. So we can build robot chains. Here on the top right, you see a balancing robot where we have these cameras observing a pan on a little pole, on a little table. And as soon as the pan starts moving, we can observe this motion of the pan and use a simple controller to counterbalance this. So we can balance the little pan on that table, because these vision systems are very, very fast. The bottom left, in a similar example, there's a chaotic pendulum, and we use a laser pointer to demonstrate that we can track the chaotic pendulum quite well and quite fast with these cameras. On the bottom right, you see there's a robotic head that has 2 of these cameras. It has 2 degrees of freedom motion on the neck and 2 degrees of freedom motion on each of these eyes. In principle, they can operate independently, so we can use this like a chameleon does and look in different directions. But here we try to mimic human motion, oculomotor control, to do smooth pursuits, to do saccades, just as humans do. So we can use a spiking system to get event input and generate motor output. Now, these are all student projects, fun projects. This is interesting to implement, but we are not yet advancing technology. We're not really getting any money out of this, let's say, from companies. Now, what has happened in the past, though, is that we use an event-based robot localization system, where we have an event camera looking up at the ceiling, and we are using the events coming from the sensor to create a map and to use the events to localize the robot on board of the map in a closed loop system, as shown here. So we use events and an estimate of where we are to build, to do event-based mapping. Therefore, we can build a map. Once we have a map or a partial map and events from the sensor, then we can localize us. So it's a chicken and egg problem that spins around to identify the robot's own position on a map while the map is being built, and building the map while the robot is trying to localize itself in the world. So this is used in, for example, vacuum cleaning robots and so on. So here is a video of how this robot performs. So here is the robot at the bottom driving around in some artificial arena. It's looking up at the ceiling. There's some structure on the ceiling, and here's the reconstructed path. So many people work on robot navigation. The real problem with traditional robot navigation, vision-based navigation, is that you need a very big computer to process vision information, to identify obstacles and objects in the scene and so on. Here we've done the exact same on a very small microcontroller. So it's doing the whole vision processing on a very small, low power, low bandwidth, low energy CPU. And the only way this is possible is because we use this neuro-inspired event format of updates rather than full images. So now we start playing out the neuromorphic principles, how brains found effective ways of representing visual information. We are not building a brain on a robot, but we are using the fundamental principles of how vision systems and brains present vision information, spike-based information of changes, so that we can use efficient algorithms to operate low power, low hardware on low hardware requirements. So this is one example. Here's another project where we want to build stereo vision system to help blind or visually impaired people to navigate the world. Here's a prototype that has 2 event cameras built in. And if you get information from 2 or more cameras, then obviously you can use stereopsis, so matching of left and right events to compute depth, distance information in the world. So with such a portable system, we are hoping to identify upcoming objects so that we can help visually impaired people to navigate safely in the world and cover a much wider range of the vicinity to allow secure, safe, and secure navigation. So how this works is as shown here. There should be videos running. Here we go. So there are 2 independent input streams from a left perception and a right perception, and we merge these, we fuse these events together so that we can infer distances, and those distances are shown here as color-coded. So when we're approaching an obstacle, this is getting red. So we can then convey the message through some other channel, for example, auditory signals, to a visually impaired person. Matching such events from left and right is a computationally intense task, both in traditional vision and neuromorphic vision. So there have been neural network approaches, for example, by David Marr et al., that describe neural networks that take a one-dimensional input from one camera and a one-dimensional input along from the other camera on epipolar lines, so that we can find potential matches between the right and the left visual input stream, and therefore identify the offset in space between the two, and therefore infer distances. So here you see a small part of a very large, possibly neural matrix that can compute such matches between left and right visual stream. It's only for one epipolar line from left and right camera. And if you have, say, 500 pixels here and 500 pixels here, you would need a 500 by 500 matrix that's potentially filled with activity with neurons everywhere, or that is at least filled in a large range of possible overlays. Now that's only for one line left and one line right. If you want to compute stereo vision across the whole image plane, left and right, you need 500 by 500 by 500 by 500 neuronal computing system, and that obviously scales very unfavorable. So if you want to compute this in a microcontroller, you run into big problems, because you cannot compute such a number of neurons that explodes with pixel input. You cannot compute such in traditional hardware effectively. And that's where I start to bridge over into neuromorphic real-time computing and control, because there's only so much we can do in traditional hardware if we want to stay in real time. Now let's look into neural computing systems. So here we see a robot on the bottom right that is driven by a neural network. And this neural network has learned to perform a task to pick up these objects that all look the same for us, but they have a blinking light that blinks at different frequencies. And it learned to pick up this object, which is at a blinking frequency that's out of sequence. So the lowest is on top and the highest frequency on the bottom. So it picked up this object and put the object at the right place. Now this looks very clumsy and very annoying and very, so everybody seeing the video would probably say, well, we could do this much better, both we as humans, but also someone who programs a robot. That's not the point. We didn't want to develop the most elegant moving robot. What we wanted to show here is that we can build a neuronal system that does everything from input to output, including the intelligence in between. Because all we've done here is we've trained the neural network, we've trained the system, showing examples of correctly ordered, correctly sequenced blinking lights. And then the system, and then we've driven the robot by hand several times to pick up objects. So we've trained it to use the collaboration between the wheels to drive somewhere and the robot arm to pick up an object. Now this sounds trivial, And if you think about it, sure, if Jens wants to go and get a coffee right now, then he will, without effort, he will stand up, use his legs to go to a kitchen, and then use the arm to grab a coffee, and then hold the coffee and walk back with the legs. So there's a natural interplay between very different motor modalities like legs and arms that are used for very different things. And you can only reach out so far before you have to use your legs to go somewhere else. This all sounds natural and without any difficulty for us, but for a robot and for traditionally programming a robot, this is a pain. This is an unsolved problem on how to negotiate, how to use the trade-off between vastly different motor modalities, and the same for vastly different sensory modalities. But neural networks solve this naturally. So does our brain, so do neural networks here. What I'm showing on the slide is that we have built simple demonstrator systems that use neural algorithms, that use neural computing instances to run these neural networks. Again, this can be a computer or this can be dedicated hardware, and that we use real-world systems, sensors and actuators, so that these computing instances can compute on some data following these algorithms. But there are always trade-offs between how complex a neural system you can run in real time, because these robots have to run in real time. We cannot upload the robot control algorithm to a supercomputer and wait for it overnight and then get back tomorrow morning to move the robot. So if you want any interacting systems, we have to do things in real time. So we'll now look into some neural computing devices that allow us to compute models of different complexity on neural-like hardware. Now here is an overview from the left, most generic, general purpose traditional computing, towards the right to examples of customized analog functionality. And there are only 4 examples here shown here. There are plenty more examples available. And if you Google briefly for neuromorphic computing, you will find many, many more examples. I just want to highlight fundamental differences. So the traditional computing system uses CPUs or GPUs. It's von Neumann computing, so it's sequential programming. You specify exactly what to do. You have all the flexibility to do, but you also have all the bottlenecks and limitations. So you have single processors or quasi-single processors that all access shared resources. For example, memory. So if you want to simulate 10,000 neurons and they all want to send spikes to each other, then there's synchronization needed. They have to wait until they all can write their data into the shared memory, which is a severe bottleneck even for GPU cards. Spinnaker, one step to the right, is a digital system. It's fully digital inside, but it's still general purpose. So you have an array of microcontrollers, of distributed independent computing units that is connected by a highly efficient point to many points communication bus. So it is still flexible in the sense that you can program any software you want. You can run any neural model you want. You can run a large number of these models in parallel because you have many, many computing cores in parallel. There's dedicated hardware to send spikes from one source to many, many targets. So that makes this computing system very efficient for neural network instantiations. Think of the stereo matching algorithm I've introduced, I've briefly mentioned a few slides back. If there are many neurons that want to communicate by spikes, the Spinnaker system will allow such. Then one more step to the right is True North. True North is customized digital hardware. There's a similar system from Intel available these days called Loihi. Same idea. It's not a general purpose computer. There's a digital system inside that is hardware designed to do exactly one computation. And that one computation is summing up spiking inputs and producing a spike as an output once you exceed a threshold. There's some few parameters you can tune, you can adjust, but that's it. You can specify connectivity in the True North system, and that's how you program the True North. So you cannot run general purpose computation. You cannot write a C program or Java or Python these days, whatever. You cannot do that on True North anymore. You can do on Spinnaker and of course on your general purpose CPU. But True North only has hardware for exactly that neural computing function. Now, this makes it very energy efficient, but it also limits the system. One more step to the right, here's Spiky as an example. That's a development from Heidelberg. This is an analog computing system. So it's no longer a digital, precise setting. It's analog electronics inside that mimic neural function. Therefore, you can get significantly more computation on small silicon area. It's much more energy efficient because you don't have to charge and discharge circuits all the time. But it's also less flexible in terms of function. It's also less reliable in terms of precise computation. It's analog systems that might be influenced by room temperature or by humidity and so on. So we have a large range of neural computing systems to choose from, starting from general purpose computers to custom analog systems. And we will look into some of them. In my lab, we have many of these available, and we decide for each of the projects what to use. We will largely use Spinnaker, that you've also heard about in previous talks, because it offers an interesting flexibility and enough neural computing power so that we can run large networks in real time. I'm not going to talk much more about Spinnaker right now because you've had a talk already about the system and we're slowly running out of time. So let me just mention that there are different flavors of Spinnaker. We have large computing boards where you can run large models on a board. Then we have computing racks that have one board here, or a cluster of boards, or a whole rack, or the whole machine room full of boards. Manchester has a very large Spinnaker setup where you can run billions of neurons, where you can simulate billions of neurons in real time in Manchester. This also doesn't help us for our robots. So what we often do is we use one such boards or a small number of such boards to run local networks, or we build individual Spinnaker standalone boards. So here is one Spinnaker chip embedded on a controller board with a microcontroller so that we can interface to spikes and we can interface to motors, so we can build standalone neural computing system where the neural computation can happen in here. So we have a neural computing device on board, we can stack more if needed, and we have an interface to sensory signals and motor outputs. So this, for example, can be used to process brain-recorded data. So we've had projects in the past where we record EEG, but also EMG as spiking intramuscular signals, and then use a spiking neural network on board of this neural computer to produce motor output. So it's spiking computation from input to output. Here's another example of what we do in spiking computation. So we have a mobile robot. We add the Spinnaker neural computer and an interface board between the Spinnaker and the robot and sensors. And we have a closed loop motor control system. So we have spiking sensors. We have as input, we have a motor wheel encoders. We have sensory inputs for translation, for motion. We have a neural computer on board, and we have motor outputs so the robot can move. And as that, we can use these robots, for example, to implement optic flow algorithms like bees do when they go around arenas. So this robot can observe the walls on the outside and use an optic flow processing algorithm to identify the speed of the walls that go by, and thereby center itself along the corridor. So this is a complete neural mechanism, a complete neural algorithm. Here's a similar approach where we have a stimulus that the robot observes, and it tries to keep both the stimulus centered with respect to itself, but also at the constant offset in the left and right eye. So it performs stereo vision computation. Therefore, it can keep distance to the object. This is all happening as neural networks on board of these computers. Good. So here's some more examples for motor control. This is how humans walk and run and interact in the world. This is amazing. I don't recommend that you walk like this unless you really train a lot. On the right, you see this is how robots interact and walk and operate in the world. There are obvious differences between the humans and the robots. This is not because it's 1 year later. I mean, humans have not advanced in 1 year this much from robots. This is because motor control is a very hard challenge and humans are very good at it. The people who have programmed these robots here, they are very interested in doing very good because it's been the DARPA Grand Challenge. There was a $1 million US dollar price tag attached to it. So they really tried hard to get these robots. And I'm also not trying to make fun of my colleagues in the robot departments. It's really a hard problem. We have to understand that. And now in the long run, we would like to get compliant actuators. We would like to get muscle-based systems because the suspension of muscles, this will help us a lot compared to the stiff motors and actuators in these robots. So we are trying to build muscle-based robotic arms and control these robotic arms with a long-term goal to go into motor prosthetic devices. So that's a long-term vision that is ahead of us. Where we are now is we use cerebellar motor control to do fine-trained motor activities. So we're trying to move this type of robot setting, this type of robotic arm that has muscles, artificial muscles in here, so motors and springs, but no stiff joints, no stiff gearboxes. And we use a cerebellar network to control this and to compensate for errors in the system, to compensate for non-linearities, to compensate for unexpected behavior, to compensate for non-linear spring dynamics, for everything that you can learn in such a physically compliant system. That again, one day we hope to be able to use in prosthetic devices. Now we're getting a bit closer to what we do in HPP. So there's a section called Physical Neurorobotics. Now there's this work package 3. There's tasks where robots interact with the world. There's a large robotic simulation environment called the Neurorobotics platform, where we can simulate robotic arms or whole mobile moving robots. We have wheeled robots and so on. So we operate these simulated robots with large neural networks. This can be lower than real time because we can slow down the simulator. But then again, it's only a simulator. In the end, we want to go to real robots. So we have a project for this robotic arm in real worlds, in a co-working scenario with a human, so that this robot arm is supposed to interact with a human. We have physical robots like a mouse, a physical robotic mouse that should walk and interact in an environment, to climb up places and touch buttons, whatever mice do, look for cheese. But in the end, we want to have a neural controller. We want to have neural networks controlling this mouse device from sensory input, event cameras or touch buttons or foot pressure sensors, up to generate motor outputs. So this now is a complete closed loop system that relies on all the neuromorphic computation so that we can get it in the available space budget, power budget, and complexity. But where is neuromorphic computation here? So what I really point out here is that we are working on a project to get the Spinnaker 2 chips, the next generation of these, as standalone modules integrated into the robot mouse. So then we have a standalone device. There's one more slide about the robot project. I probably just skip that. We can read up or you can catch up on HPP presentations. What we've done in the past is a robotic arm that picks up objects, explores the objects, and manipulates or moves and throws. What we're doing now is we're working on an interactive task where a robotic arm should co-work with a human. So we have PhD students, Jens and or Juan, to work with this robot. And of course, the robot should not kill these students. It should be a gentle helper. It should be friendly. It should be a natural interaction between the robot and the student. And therefore, we need to get things arranged in real time and make it able to sense and perceive what the human does, all this in neural computation. So the second part, neural computing systems, is really about getting a closed loop setup, energy efficient, scalable, so that we can run the neural algorithms in real time, so that we can interpret sensory signals, we can create motor outputs, and we hope that one day we can build devices. We're working towards devices that help you in everyday tasks. This could be neuroprosthetic devices, as shown here, or this could be a robot that helps you to go shopping in a supermarket and loads and unloads your devices, or this could be a robot that helps in your household in interactive settings. Now, with this said, I've spent a lot of time on presenting neural principles for real-time systems engineering. I am done with what I want to say. Remember, there's this web page. It's vastly outdated, but you get the basic ideas of what we do. If you have more questions, now is time for questions. Please absolutely ask or comment. And there's also always questions that you can ask Jens or Juan or myself in the upcoming days or weeks. Thank you very much for your attention. And now I'm all open for questions.